I'm excited to introduce you to our next keynote speaker, Monica Nayan Agrawal, who recently completed her PhD in computer science at MIT. Monica will describe how large language models can be used to parse clinical text with only a minimal amount of supervision. Thank you for joining us today. Over to you, Monica.
Hi everyone, I'm Monica, and today I'll be talking to you about large language models for parsing clinical text, work that I completed during the end of my PhD at MIT CSAIL. And today I'll be discussing work that was published at EMNLP 2022 last December in a paper called Large Language Models or Few-Shot Clinical Information Extractors. And this work was joint with colleagues Stefan Hegselmann, Hunter Lang, Yoon Kim, and my advisor, David Sontag. So to start off with, I want to talk about why clinical information extraction is so important. The data in electronic health records can help us answer questions in personalized medicine that clinical trials can't, like what treatment is best for you, a specific patient with specific comorbidities, and past history. Unfortunately, many of the important variables we need to answer questions like that are not found in structured data. These are variables like treatments the patient has taken, outcomes of taking those treatments, and side effects of those treatments. Instead, they're trapped in messy clinical text like PT will DC carbo IA for TNBC. Therefore, extraction requires multiple hops of logic. So let's take this example, PT will DC carbo IA for TNBC. So first, if we want to understand this, we can first identify the terms that are medical in nature, but then we have to understand what they're referring to in clinical ontologies. So TNBC usually only means triple negative breast cancer. And once we have that decoded, we can tell that carbo probably refers to the chemotherapy carboplatin, since we're dealing with a cancer patient, and not the cream carbodome. And once we know we're dealing with chemotherapy, we know that IA is probably intra-arterial and not intra-articular. And since we're talking about a medication, the DC probably means discontinue as opposed to a DC current or a hospital discharge. And finally, here we can tell that PT means patient and the subject is not something like physical therapist. And now once we've done this first level of logic, we can then start to parse the sentence and understand what the subject is and how they all relate to one another. However, clinical information extraction with NLP has largely been quite difficult because labeled data can be prohibitively expensive. And this is for a few different reasons. First is labels in clinical NLP are not a natural byproduct of clinical care, the way they often are for fields like medical vision. And as a result, these labels have to be created as part of a separate process. Creating labels for doing tasks like this requires a significant amount of domain expertise. So it's not something that, for example, could be done by third parties without clinical knowledge. And finally, it's really difficult to share clinical notes and the corresponding annotations across institutions due to the sensitivity of the text in electronic health records. And taken as a whole, this has really impeded progress in clinical information extraction since it's really hard to get large labeled data sets. So the status quo in clinical NLP has been the following. First, we define a task. So for example, for a patient phenotyping task, we might want to ask, does this patient have some specific condition A? The next step is to create labeled training data. So for each input X, some note, label the output Y of whether they have the condition. We then train a model to output Y given X, and this could be something like a logistic regression. And once we have a trained model, we can use that model on new inputs. However, step 2 really requires the creation of labeled training data. However, more recently, there have been huge advances in language modeling that have burst onto the popular scene. So for example, we see language models being used for plagiarism, for writing articles, and for advertising. But then the question is, are they also ready to be used for medicine, since it's a very different domain? And that's what we study in our paper. So to start off with, I'm going to describe some background for in-context learning. So the traditional paradigm in NLP has been to take some input, so in this case, a movie review, a model, and then train the model to output one, for example, positive, and -1 for negative, if it's a negative review. The new paradigm is to instead not ask the model to output a number, but ask the model to output positive or negative directly, since these large language models have been trained to generate text and complete the sentence. So instead, we put the review in part of what is called a prompt, which is shown in green. And we then prompt the model to answer the question of whether the review was positive or negative. And this is much simpler to do for the model to do, since it's part of what it's been trained to do, which is complete text. Sometimes additionally, people add what's called a one-shot or few-shot example, where they give an example to the model of what they want the output to look like. And this is shown in blue. So then the question is, can this paradigm of in-context learning improve how we do clinical data mining? So there's a few challenges involved that aren't found in some other common applications. So the first challenge is the availability of clinical text. So due to patient privacy, there are likely not significant corpora of clinical notes in the training data of these large models, like GPT-3. Further, and particularly at the time the work was done, most existing label datasets were under data use agreements that precluded them from being sent over to APIs like GPTs. And as a result, it was hard to benchmark on existing data in clinical NLP. To counter this, we created our own benchmark datasets. So we re-annotated the existing publicly available CASI dataset, which was made for disambiguating acronyms, to release 3 new extraction datasets that could work in the few-shot setting. And I'll talk more about what these look like later, but there are clinical coreference resolution, medication extraction and status classification, and medication and attribute relation extraction. Each of these contains 5 examples for development. And by development, I mean prompt design, so designing how you ask the model a question, and 100 examples for test. And these have been open sourced on Hugging Face. The second challenge is obtaining structured, evidence-backed output. So let's say our goal is to list medications and their reason, dosage, and frequency as available. So our input looks like 500 milligrams of metformin BID. The expected completion might be something like medication metformin, dosage 500 milligrams, frequency BID. However, the reality, if we were to ask a model, is that it might return something that looks more like the medication taken is metformin for the reason of diabetes at a dosage of 500 milligrams. And this is problematic for 2 reasons. The first is the narrative format, since we now have to turn the reality into something that's usable for downstream tasks and that we can import into a JSON. But the second issue are hallucinations. So for example, here, the model, in this toy example, the model assumes that the metformin is taken for diabetes, which is the most common indication of metformin, but not the only indication of metformin. For example, metformin can also be taken for pre-diabetes and PCOS. And what we don't want is the model to populate our database with the most likely indication instead of what's listed, since that could really throw off our data. So if we were to do something naive with a 0-shot prompt, we might get something in blue, like what I showed you before. And then to get to the blue, to the nice JSON we want, would require complex post-processing. And we call this post-processing procedure a resolver. However, instead, if we use our approach, we find that it can be much simpler. So here I show a one-shot example with guidance. So in the one-shot example, we provide the model with the framework of how we want them to present this. And more importantly, we show it that we want it to be quoting from the original text. And as a result, it's less likely to output something like diabetes that is not, in fact, a quote from the original text. We also provide guidance, in this case, just a bullet point. And what this does is it shows the model that we want to list, and it keeps it from saying something like, I don't know. And once we have something like what's shown in blue, there's very little post-processing that has to be done to get to the JSON format. And that way the resolver, as we call it, can be much, much simpler. The third challenge are deployability concerns. And these are concerns like HIPAA compliance, the unwieldy size of models, and these are things that are actively changing at the moment, but also things like sensitivity to wording. So the exact wording of the prompt has been shown to lead to really different results, as well as model miscalibration when the calibration probabilities from the model are available, which is not true for many open source models today. So this is an example from ICML 2021, where they show that depending on exactly what examples you provide it and in what order you provide those examples, GPT can have vastly different performance. So our solution uses weak supervision plus distillation. So let's say we have a set of publicly available data that we can use, and that's shown in blue. We can run that through the large language model and get its classification outputs. So in this case, I'm showing each class as a different color. The next step is to identify confident outputs. So how can we tell where the large language model is confident? And this was work that I'm not going to be discussing today, but you can read more about it in Lang et al. In the citation shown at the bottom. And now we can train a much smaller model, so something like a BERT or a BERTA, or something that's much easier to do on common infrastructure, but only train on those outputs where our method found that the model was confident. Importantly, we're not using the model's own sense of confidence. And now we can run this smaller model on an unlabeled data set, here shown in green, to get labels. And we can actually run it on the original blue data set and actually improve on the performance of the large language model alone and correct places where the large language model had not been confident. So now I'm going to start talking about some results. So the first task we look at is zero-shot clinical acronym disambiguation. So the input here is a clinical text snippet and an overloaded acronym. And the output we want is a multiple choice expansion of that acronym. So in an example, you have a clinical note that might say CTA, and what we want as output is knowing that the CTA shown here in orange means clear to auscultation. So what we find is that in the zero-shot setting, where we give it no examples, that GPT, shown in blue, can largely outperform the existing zero-shot baseline, which was a language model trained on mimic data. However, if we then use the weak supervision and distillation approach that I showed you 2 slides ago, we can do even better, finding a 10% or so boost on F1, which describes disambiguation power. Further, we can now transfer to mimic, which we would not at the time have been able to send to GPT, and we find that we can do about just as well or better than the zero-shot baseline that was trained on mimic itself. The second task that we look at is biomedical evidence extraction. So the input here is a clinical trial summary from the PICO dataset, and the output is a list of interventions and arms of that trial. So here's an example in which what we desire is a list of the different arms of the trial, shown in orange. And what we find is that on a set of 20 manually scored clinical trials, GPT-3 was able to perfectly capture 85% of them. In contrast, a supervised PubMed BERT with Oracle Coreference could only get to about 35%, often missing things like the control group. In task 3, we study clinical coreference resolution, which is often important for tasks like summarization. So in this task, we are given a snippet and a pronoun, and our goal is to output the antecedent of that pronoun. So for example, if we have a sentence like the one shown here, the task might be to understand what this is referring to later in the sentence. And our goal is to understand that this is referring to the current regimen for MS. And this task is important for ensuring that in doing summarization, we understand what's being referenced at each time. And what we find is that GPT, shown in green, can greatly outperform a baseline that was supervised on many non-clinical data sets, and that we can do much better than we would do in the zero-shot case, where we don't use our guided approach. And in that case, the resolver requires 50 lines of code as opposed to 1 line of code. However, further, we find that we don't necessarily need to give it a correct example in the guided approach versus just showing what structure we want. The next task we look at is medication and status extraction. So the input is a clinical text snippet, and the output is a list of medications and their status, by which I mean, is the medication actively being taken by the patient? Is it discontinued, or is it in some other neither category, like an allergy? So an example would be this assessment and plan, where they recommend Citracel and have decided to DC the colace. And what we want to understand is not just what are the medications mentioned, but the fact that the Citracel is active and the colace is discontinued. And here we find that compared to a SciSpacey baseline, we can do significantly better at recall and precision. And again, compared to an approach without the guidance, we can have a much simpler resolver with 8 lines of code needed instead of 32, and we can also outperform. Looking at whether it gets status correct, we find that we can do significantly better with GPT in green compared to doing something like a few-shot fine-tuning method like T-few. Finally, we look at medication and attribute relations, where the input is a clinical text snippet, and the output is what I partially described before, which is medications, dosages, routes, frequency, reasons, and durations. And here we look at it from 3 different angles. One are token level labels. So for each token, does it fall into one of those classes? Phrase level labels, in which we chunk together tokens that belong to the same entity. And finally, a relation extraction setup, where we actually don't just identify the entities, but also how they relate to each other. So an example of that relation extraction setup is something where we see what's here, where we don't just identify the aspects, but the fact that all of those go with aspirin. And what we find in green is that we can do significantly better than a baseline that was supervised on a different clinical data set, which was a PubMed BERT with a CRF on top. So one large question are, what data are these large language models learning from? And this is something that's hard to answer without access to the underlying data, but as an approximation, we classified sources of colloquial clinical jargon like FX and fracture in a subset of the common crawl data, which is a crawl of the internet. And this is work that was not part of EMNLP, but is found in my thesis. And what we find is that for a set of colloquial clinical jargon like FX and fracture, they're found across a multitude of sources. So not just research articles, but also patient health resources, commercial health websites, clinician forums, and patient blogs and forums. And specifically for certain terms, they occur far more frequently in certain sources. So for example, 43% of the mentions in our subsample for QHS and bedtime came from patient health resources. And for 41% of the mentions for carbo and carboplatin in our subsample came from patient blogs and forums. And this indicates that it's really important to explore different data sources when training these models. So in conclusion, despite not being trained for the clinical domain, Large language models can do quite well at a variety of tasks. However, naive application of these methods is insufficient. Guiding the structure of the generation is key for structured data output, but correct examples aren't always necessary. And for classification tasks, weak supervision and distillation can improve performance and enable transfer to private data. Thank you, and I'm happy to take any questions.